Today we're going to talk about systems of nonlinear equations. This is a little bit of a detour from conic sections. I will motivate it with a conic section example, but it's not directly related to conic sections. So let's start with an example. The example is find the coordinates of the intersection points, or the intersections, of the line y plus 2 is equal to 2x, and the circle x squared plus y squared equals 25. Now, you don't need to draw a picture to solve this problem, but I will draw a picture just to sort of convince you that what we're doing makes sense. So let's sketch these two objects that I've described here. We have a line whose equation is y plus 2 equals 2x. If you solve this for y, you'd have y equals 2x minus 2. That's a line with y-intercept negative 2 and slope 2. So maybe it looks something like that. Okay, so that's our line. This is a circle. H and K are both 0, so it's centered at the origin, and the radius is 5. So maybe that's something like this. The objective is to find the intersections of those two objects. In other words, find that point and find that point. So how do we do that? Well, do you agree? Well, I guess you can't answer the question, but I would argue that the line, this line right here, is the set of all points satisfying this equation here. That's what this line is. It is the set of all points which satisfy that equation. And the circle is the set of all points which satisfy this equation. Okay? Now, the thing to notice is that the intersection points are on the line, and they're also on the circle. Because the intersection point is on the line, that means it satisfies that equation. And because it's also on the circle, it means that point also satisfies this equation. Therefore, the intersection points are exactly the points which satisfy both equations. So to find the intersection points, what we have to do is solve the system of equations given by y plus 2 equals 2x and x squared plus y squared equals 25. All right? So that's the procedure. Now, this is a system of equations, two variables. How do you solve a system? You probably remember from whatever, Algebra 2 or geometry or something, that there are two methods for solving systems of equations. One of them is elimination. Remember where you add one equation to the other and the variable disappears? That's one method. The other method was substitution. Elimination mostly will not work for these kinds of problems. Substitution is what you have to use. Substitution is really the grown-up method for solving systems of equations because it always works. So here's how substitution works. So we're going to use substitution, okay, to solve this system of equations. And the way that works is your first move is you have to isolate a variable. And then once you've done that, you're going to stuff that variable into the other equation. So let's take a look at this system here. The first move is we have to get one of the variables by itself. Technically, it doesn't matter which equation you use to do that. You could solve for x in this equation, or you could solve for y in this equation, but usually there's a choice of equation and variable that is easiest to work with. In other words, if you compare these two equations here, it's much easier to isolate a variable in this first equation than in the second equation. To isolate a variable here, you would have to take square roots, and it would be really nasty. Here, that's a linear equation, much easier to isolate a variable here. So we'll use this equation here to isolate one of our variables. You could choose to solve for x, or you could choose to solve for y, and it doesn't really matter, except often one choice is easier than the other. In this case, if you look, if you solve for x, then you're going to wind up with fractions. You would have to divide both sides by 2. We don't want that. So instead what you should do is solve for y, which is easy. You just subtract 2 from both sides. So I'll use that equation to solve for y. So I have 2x minus 2. And then what I can do is I can take this expression and stuff it into the other equation, right? So in other words, I'm going to replace this y right here with this whole expression right here, because y is 2x minus 2, so of course I can replace y with 2x minus 2. So stuffing this expression into the other equation, I obtain x squared plus, and now I'm replacing this y here with this expression, so I have 2x minus 2, quantity squared, is equal to 25. This equation is now just one variable, so we can solve it. It's a quadratic, although it's definitely not in any kind of conventional form. You should start by multiplying out this, this squared term here. So remember what 2x minus 2 quantity squared really means. It means 2x minus 2 times 2x minus 2. Don't make the mistake of thinking that you can just distribute the 2 to these two terms. Exponents don't distribute across plus and minus. We have to FOIL this whole thing out, multiply it out. So 2x times 2x is 4x squared. 2x times negative 2 is negative 8x. Negative 2 times 2x is, sorry, it's not negative 8x, it's negative 4x. And then negative 2 times 2x is again negative 4x. Finally, negative 2 times negative 2 is plus 4 equals 25. We can simplify this, so we can put the two quadratic terms into one term. That gives me 5x squared. The two linear terms will combine into minus 8x. And then because this is a quadratic equation, generally speaking, what you should try to do is put everything on one side and attempt to factor. So I might as well move, while I'm at it, this constant term over to the left-hand side. I already have a 4 here, so if I subtract 25 from both sides, I'll have a minus 21 equals 0. Okay, so this is a quadratic equation in standard form. You can try to, so if you remember, the fact that we have a 5 in front of the x squared term is kind of bad news. It means that the usual procedure of factoring this thing doesn't really work. This expression can still be factored, but the procedure is a bit more annoying. It's factoring by grouping. If you remember how that works, great. But if you don't, then you can just use the quadratic formula, which is what I'm going to use. And by the way, even if you really feel confident in using factoring by grouping to factor something like this, factoring by grouping, if this quadratic has irrational roots, then factoring by grouping won't work, and you just won't be able to factor it. So you might as well just use the quadratic formula when you're not sure if it even has rational roots. So let's just remember what that is. It's x equals opposite of b plus or minus square root of b squared minus 4ac all over 2a. So I just have to sort of compare that with my equation here. So I have x equals opposite of b, that's positive 8, plus or minus square root of b squared, that's negative 8 squared, which is 64, minus 4 times a, which is 5, times c, which is negative 21, all over 2a, which is 2 times 5. A quick comment, a lot of people, when they use the quadratic formula, try to get sort of clever and simplify the expression under the radical in their head before they even write it down. Generally speaking, this is a bad idea, and people tend to make a lot of mistakes doing that, especially with the multiple minus signs floating around in this expression. It's easy to get a sign wrong. So just plug in the numbers carefully and then evaluate in the next line. So what is this? So I have 64. So this expression here, because of the two minus signs, is going to be a plus. Well, plus what? 4 times 5 is 20, times 21 is 420, all over 2 times 5 is 10. Okay, so I've got 8 plus or minus root 64 plus 420 is 484 over 10. Fortunately, 484 happens to be a perfect square. It's the square of 22. So this is 8 plus or minus 22 over 10. So the plus or minus yields two different solutions. One is 8 plus 22 over 10, which is 30 over 10, which is just 3. Right? So that's one value for x. And the other is 8 minus 22 over 10, which is negative 14 over 10, which is negative 7 over 5. So these are the two possible values for x, but we're not done because, remember, we had a system of equations. A solution to a system of equations consists of an x value and an associated y value. What we have here are just two x values. Associated with each of these x values is some y value that we also need to find. And the way that you do it is you go and you plug these back into one of your original equations. Really, any equation will do, but work with the easiest equation you can. I like this one because it's already solved for y, so I'll plug my x values back into that equation there. So I'll just do it right here. So my first x value was 3, so I'll plug that into this equation here. I have y is equal to 2 times 3 minus 2, and that's 4. So the y value associated with x equals 3 is 4. So I want to represent that as a pair of x, y values, so 3 comma 4. Okay? And by the way, that would be one of the points of intersection, probably this one, thinking about the quadrant. And then I have this other x value, negative 7/5. To find the y value associated with that one, I also plug it into this original equation here. So I have y is equal to 2 times negative 7/5 minus 2. So that's going to give me negative 14/5 minus 2, which is, I think it's negative 24/5. So, right, so what is the xy pair? So the x value that we were using here was negative 7/5, and the associated y value is negative 24/5. And so I guess that would correspond to, this point down here. Very quickly, a lot of times students, when they're solving systems of equations, they don't write their xy values as pairs like this. They just sort of write, oh, x is 3, x is negative 7/5, and then they'll write y is 4, y is negative 24/5. That is really not acceptable. The thing is that this x value is associated with only one of the y values. It's associated with 4 and not the other one. So, to emphasize the fact that each x value is associated with one and only one of the y values that we found, you really have to write them as pairs. Otherwise, I don't know which x values are associated with which y values. So it's important to do that. Okay.